In this problem, we are given a derivative graph. It is the derivative of the function f. So, like in the warm-up, we will be doing derivative analysis. In part A, they want us to find the relative maximum of the function f, and we can only see the derivative graph to make that determination. You might notice here that they do not want us to consider the endpoints, so they left them out here. So we know we will have a relative max where the derivative goes from positive to negative. That occurs here, and that also occurs here. See, above the x-axis means f prime is positive, and below the x-axis means f prime is negative, since we are looking at the derivative graph. So we write here, f has a relative max at x equals negative 3, also at x equals 4. What is important here is how we justify this. So we're going to say, because it is really important to say this first part, f prime of x equals 0. And some people skip over this part here, and they won't receive full credit. So f prime of x equals 0, and the derivative goes from positive to negative at these x values. Now in part B, it wants us to find the points of inflection of the graph of f. Again, we don't see that graph of f, we see the derivative. So let's start off with some visualization, and then we'll explain more conceptually. It's going to occur at the vertices of the derivative graph, so at x equals negative 4, x equals negative 1, and then again here at x equals 2. That's where they're going to occur. Now we have to explain that a little bit more. Now remember, a point of inflection, if we were actually looking at a function's graph, and the point of inflection is where it changes concavity. And let's think of it more conceptually what concavity is. Let's look at this. Negative 5 to negative 4. What's happening there? Well, the derivative graph is getting bigger, or the derivative graph is increasing. And since the derivative is increasing, the original graph of f is concave up. So we would also have concave up here. Now, let's take a look at another portion of the graph. Here, between x equals negative 3 and x equals negative 1, the derivative graph is decreasing, which makes the original function concave down, or the second derivative negative. Also here, what's happening here? The derivative is decreasing, makes the second derivative negative. So at these points in red, the derivative goes from increasing to decreasing, or vice versa. Or said differently, the second derivative changes sign. So we'll write because f double prime changes sign at these x values. As an alternate, we could simply say that f prime of x changes its increasing / decreasing behavior. That's more visually what we're looking at. But do remember the slight cheat, I guess, if you will. It's going to be the vertices of the derivative graph. Part C, they want an interval where both the graph of f is concave up and also has positive slope. This sort of combines A and B. So positive slope means above the x-axis, and concave up, as we just discussed, means that the second derivative is positive, or said differently, the first derivative is increasing. I've highlighted in purple where the function is both positive slope and concave up. We will write negative 5 to negative 4 using parentheses. Concavity always uses parentheses. In union with 1 to 2, some will say this as intervals, or you can say this as one interval combined with a union. And this is because on this interval, both, now we need both of these qualities, both f prime of x is greater than 0, visualized as f prime graph above the x-axis, and f double prime of x is greater than 0, visualized as the f prime graph is increasing. And we needed both of these qualities simultaneously. In part D, we want to find the absolute minimum value of the function f on a closed interval, and so we will use the closed interval test here. If you recall, we first consider interior critical x values. It's not okay to just state them. We want to state why they are critical x values interior. I'm going to highlight them. We have -3, x equals -3, x equals 1, x equals 4, and we want to say why they're critical. We don't want to just mention them, so we will say f prime of x equals 0 at x equals -3, x equals 1, x equals 4. And we also want to note the endpoints are always critical x values on a closed interval. The next step in the closed interval test is to compute the function f at all of these criticals. So we need f of -5, we're going to need f at -3, f at 1, f at 4, and finally f at 5. Now, a key element to this problem is that one of these is given. In fact, one of them has to be given, otherwise we can't find the others. In this case, f of 1 is equal to 3, and I know that because it is given in the problem. And I also know that f of -3 will return a relative maximum because we found that in part A. In the same manner, f of 4 will return a relative maximum. So those are going to be out because we're trying to find the absolute minimum. And here is the awesome part about the problem. We have to figure out what f of -5 is. So we're going to do the fundamental theorem of calculus part 2, I like to say in disguise. We're going to take from -5, the lower bound, to the upper bound of 1, and I'm using 1 because I have information about that. F prime of x, now the fundamental theorem of calculus here says that will return f at 1 minus f at -5, the fundamental theorem of calculus part 2. On the left-hand side here, we will find this answer by appealing to geometry. Here we have half of the small semicircle, so 1/2 pi, the radius would be 1. And then I'm going to subtract the larger semicircle, so I have 1/2 pi times its radius squared, and I have that. Now f of 1, we know that answer, that was given as 3, minus f of -5. And then I use some good old algebra to compute f of -5. F of -5 is going to be 3 plus 3 pi over 2. That's what this expression simplified to be negative, but I brought it over to the right-hand side. Now we're going to do something similar to solve for f of 5. This time the integral I want to set up is going to be the integral from 1, I'm using that 1 again, to 5, f prime of x dx, which is the antiderivative of the top bound minus the antiderivative of the bottom bound. We're going to appeal to geometry here on the left. And so that'll be big triangle 3 minus little triangle of 1/2 equals f of 5, the thing we're trying to find, minus f of 1, which we know is 3, coming over here. That means that f of 5 is going to equal 3 plus 3 minus 1/2, or 6 minus 1/2. I'll go ahead and write that over here, 6 minus 1/2. So what is the absolute minimum value? The absolute minimum value is 3. Please don't say 1, that's where the absolute minimum value occurs, but the actual absolute minimum value of the function is 3. We do not have to say by the closed interval test, we just have to illustrate the closed interval test as we did here.